Chapter 5, molecules and compounds. We've talked about atoms, talked about the structures of atoms. Now we're going to talk about how they combine to make up molecules, which make up almost everything. I say almost everything because some things are just atoms. So, like I said, everything is made of molecules or atoms, sometimes both. Well, actually, always both. Ordinary table sugar is a compound. So it's if you had just pure table sugar, it would be a pure compound made of just sucrose molecules. So it's a pure compound made of sucrose molecules. Sucrose, or a sucrose molecule, contains carbon, hydrogen, and oxygen atoms. And it contains those in a specific ratio. And the properties of an entire sucrose molecule is very different than carbon, hydrogen, and oxygen, right? Because hydrogen and oxygen are both gases. Table sugar is not even a gas. Carbon is, well, charcoal is made of carbon. Pencil lead is carbon. Also, this is, a little surprise is the next slide, but sodium is this sort of gray metal, and chlorine, which is this green gas, both of these very toxic. Sodium, hyperreactive, but they form sodium chloride. So when combined, they're table salt, which is delicious. So combining atoms together can completely, and most of the time does completely change their properties. So something like sodium and chlorine combined together to sodium chloride gives it different properties. Most substances we encounter in everyday life are not elements, they are compounds. And like I said, free atoms are super rare. Even things like oxygen, nitrogen, like very common gases, they don't exist as single atoms, they exist as diatoms. So di meaning two atoms. And these compounds are what we call molecules, which we'll get into in a second. They're different from mixtures, right? Because we talked about what mixtures are. They're just random assortments of different things. The proportions don't matter. In compounds, molecular compounds, the elements combine in fixed, definite proportions. Mixtures can have any proportions. One example being the ratio of hydrogen to oxygen in a mixture, so like in a balloon, is going to vary. If you use like a pump, like a bike pump or something to blow up a balloon or a raft, it's going to have a lot more oxygen than if you use your breath. But it's still going to fill it up. It's still a mixture, but the proportions don't matter. So it's just a mixture. Instead, in like water, we have hydrogen and oxygen, but they're combined in a specific ratio. So for any amount of water, you'll have the same ratio of oxygen to hydrogen. There'll be 2 hydrogen atoms for every 1 oxygen atom. It was Joseph Proust who formally stated the idea that elements combine in fixed proportions to form compounds. It was kind of wild that that's only like, I mean, 1700, to 1800 is a long time ago, but also like there's a lot of stuff going on even before that. This is called the law of constant composition. All samples of a given compound, water, table sugar, have the same proportions of their constituents. Specifically, right, compounds. So we took 18 grams of water. This was actually in chapter 1. There was an example of this, trying to look at trends in trends in data. We had water. So here we got 18 grams of water. If we decompose that, so like I mentioned last week, I think it was, if you take a 9-volt battery and put it in salt water, you can decompose water at home and create oxygen and hydrogen. If you did this with 18 grams of water, and you could somehow capture and weigh that oxygen, you get 16 grams of oxygen and 2 grams of hydrogen every single time. If you decompose 18 grams of water, you get those specific ratios. It's this 8-to-1 ratio. So ratios really are where you divide one thing by another thing. And I can tell you the relationship between those two things. So there's 8 times the mass of oxygen. Yeah, constant composition with respect to mass because they're composed of atoms in fixed ratios. So say we have 2 samples of carbon monoxide obtained from different sources, and they're decomposed into their constituent elements. One sample produces 4.3 grams of oxygen and 3.2 grams of carbon. The other sample produces 7.5 grams of oxygen and 5.6 grams of carbon. Are these results consistent with the law of constant composition? I think this is a good problem and just for general word problem solving techniques. Make sure that you keep the numbers together that are related. So for example, right, in one sample, I use 2 different colors for this, produces 4.3 grams of oxygen and 3.2 grams of carbon. So that's our one sample. The other sample is 7.5 grams of oxygen, 5.6 grams of carbon. So we want to keep those 2 separate, right? We don't want to mix up our data. So very similar to any other problem, we could write down these things that were given, 4.3 grams of oxygen and 3.2 grams of carbon. Be careful not to spell that with the B before the R. And then 7.5 grams of oxygen and 5.6 grams of carbon. So this is, it doesn't call this one sample 2, but we'll call it sample 2. This is sample 1. So we're trying to determine, well, the question is, are these results consistent with the law of constant composition? We could also think about this as, are these both carbon monoxide? So what should be true if they're both carbon monoxide? Starts with an R. Yeah, the ratio should be the same between them. So like I said, ratios are one thing divided by another thing. So as long as you do that consistently, so in this case, I'll do oxygen divided by carbon. Usually you do the larger number divided by the smaller number, because then you get a whole number rather than a percentage. So if we get 4.3 divided by 3.2, let me read. So 4.3 divided by, be consistent, I use this, 3.2, that equals 1.34375. And then for our other one, we'll do 7.5. Again, because in the first one, I did oxygen divided by carbon. In the second one, I need to do oxygen divided by carbon also. So 7.5 divided by 5.6. And we'll get 1.3392. I'll stop at 86. So is this consistent with the law of constant composition? It's pretty close. This is close enough, especially since if we look at our significant figures here, we really should only be considering 2 sig figs for each of these. So this first one would be 1.3, and our second sample would be 1.3. So there's always some amount of error in experimentation. And these are really, really close, right? Like this is 1.339, very, very close to this 3.4. But this is where y-sig figs are important. So this is consistent with the law of constant composition. And we could say that if we know that our first sample is definitely carbon monoxide, then the second sample is probably carbon monoxide. So I've written out a few chemical formulas as we've been going through these things. So the chemical formula represents that specific ratio between the elements in a compound. So carbon monoxide, from our previous question there, will be carbon. And we'll learn this in this chapter. Monoxide means mono oxide. Mono is one. So it's a carbon, single carbon, and a single oxygen. So every single carbon monoxide has this ratio 1:1 of carbon and oxygen. If we have more than one thing, we can use subscripts, and it's very important to write these as subscripts. We can use those subscripts to indicate if there's more than one. So in water, we have 2 hydrogens. So it's H subscript 2 and O. And then always in chemistry, yeah, I think always in chemistry, if there's a 1, we just leave it off, it's implied, right? Because we wouldn't write oxygen here if there were 0 oxygens. So it's enough to say that there's an oxygen there, we don't need to write the 1. So this is also why it's important to know the chemical symbols. So you can look at this and know that it's 2 hydrogens, 1 oxygen. So we talked about table salt, which is sodium chloride. Again, because these don't have subscripts, they're implied. So it's 1:1 ratio. 1 sodium, 1 chlorine in table salt. Well, 1:1 ratio between them, right? It's going to be lots of sodium, lots of chlorine, but as many chlorine as there are sodiums. For carbon dioxide, you hear a lot about it, is greenhouse gas. Carbon di again, meaning 2. Oxide, meaning oxygen. There's 1 carbon and 2 oxygens. 2. So it's a 1:2 ratio. Table sugar, a lot more complicated, has 12 carbons, 22 hydrogens, and 11 oxygens. Now, as it turns out, it's also the arrangement of these and how the different atoms are connected matters a lot. You could do a lot of different structures with that number of carbons, hydrogens, and oxygens. So the chemical formula doesn't tell us anything about that. But that's really more organic chemistry anyway. So the subscripts in a chemical formula are part of the compound's definition. If you change those subscripts, you get completely different compounds. So one of the chemistry jokes is a chemist walks into a bar and orders a glass of H2O. A second chemist walks in and he says, I'll have a glass of H2O too. And he takes a drink from his glass and he dies because he was not served water, which is H2O, but he was served hydrogen peroxide, which is H2O2. So the number of the subscripts are important. We don't change those unless there's a chemical reaction going on. Just like CO2, carbon monoxide, CO, and CO2 are different. Yeah, and carbon monoxide, that's why you should never run your car in a garage or use a gas burner inside to warm up your house or apartment. Generates carbon monoxide, which is deadly. So keep that in mind. These are only going to change if we have a chemical reaction taking place. Otherwise, That is the definition of that compound. I write this out. Water. So when we are, because this will be important, and this is part of the nomenclature worksheet, is practicing how to write out elements. In chemical formulas, we list the most metallic elements first. So if you remember from the periodic table, when we talked about sort of patterns on the periodic table last week, we have the whole periodic table, or not, I can't zoom out all the way. All of these on the left side are all metals. So the farther to the left it is, the more metallic it is. So if you get any of these elements, they'll go first. Then you'll put the nonmetals next, or metalloids as the case may be. This is important also because in compounds that do not include a metal, the more metal-like element is listed first. So in that case, going back to the periodic table, again, just like for the metals, farther left is more metallic. For the nonmetals, it's like, excuse me, neon would be the least metallic. Carbon or boron would be most metallic in that row. It's going to go left to right or right to left, increasing metallic qualities on the left. So sodium chloride, whoops. Sodium chloride would not be written chlorine sodium because Na is on the very left side of the periodic table. So it's more metallic. N2O, we go back to the periodic table. Nitrogen and oxygen. Nitrogen is farther left than oxygen, so nitrogen goes first. Oh, good. Completely forgot that this was here. So if you want just an actual list of what order you should put things in, here's your list. I think the one exception that we'll really have is hydroxide, which we really won't talk about too much until later. That's where oxygen is written before hydrogen, and that's just a historical exemption. Probably the only one we'll cover. So if you had elements made up from, if you had compounds made up from these elements, if you had carbon and phosphorus, you'd write the carbon first and the phosphorus second. If you had nitrogen and iodine, it would be nitrogen and then iodine, not the other way around. Okay, so let's do a little practice. If we had a compound containing 2 silver atoms to every sulfur atom. So what's the symbol for silver? Ag. And then the symbol for sulfur? S. Actually, sure, I'm going to put this over here. Ag, S. So which of those should go first? Which one's the most metallic? I wish there was just a periodic table in here. Yeah, so Ag is truly a metal, and then sulfur is up here. It's a nonmetal. So this would be 2 silver atoms. So we'll get Ag2 per every, or to every sulfur atom. So Ag2S. We have 2 nitrogen atoms to every oxygen atom. So symbol for nitrogen, oxygen. So which one goes first? Yep. This is farther left, or we could go back to this previous and see that nitrogen's over here, oxygen over here. So then we have 2 nitrogen atoms to every oxygen atom. All right, N and O, and then we'll have 2 nitrogens. Just make sure that you write those as subscripts. With a compound containing 2 iron atoms to every 3 oxygen atoms, iron is Fe. We've done oxygen, that's O. So which one comes first? I heard an Fe out there. All right, so we'll get iron. We'll have 2 iron atoms to every 3 oxygen atoms. So the number of each atom in the compound is the subscript to the bottom right. If there's no subscript, it's 1. All right. Polyatomic ions are special ions. Remember, we talked about ions. We have cations and anions. Cations having positive charges, anions being negative charges. Most of the polyatomic ions are anions. They have negative charges. They're special because they're made up of multiple atoms. And in chemical reactions, they operate as a group, sort of as a single unit. Which is why there's the list of polyatomic ions to memorize. So these ones that act as a unit, the polyatomic ions. If we have 2 or more of the same type of polyatomic ion, we don't just add more of each of the individual elements. You treat it, again, as a unit. So here, nitrate is NO3 minus. Because we have 2 nitrate groups here, we put that in parentheses and then use a subscript outside of the parentheses to indicate how many nitrate groups there are. All right, so NO3 is our polyatomic ion. If we want 2 of them, have to write it like that. If you have 1 of them, you just leave the parentheses off. So something like sodium nitrate would be NaNO3. This is why I have you memorize the polyatomic ions. So you need to just know that this is nitrate, that it's a polyatomic ion. All right. So determine the number of each type of atom in the following formulas. This is important. This is one of the things that gets missed a lot. So for this one, does anybody know what that, well, it's a polyatomic ion, right? So it's this one. Does anybody know what it is? It's formed from sulfur. And we'll learn rules about oxygen counts later, but sulfate is this polyatomic ion. So it's sulfur, polyatomic ion, sulfate. Just change the ending. So if we want to count the number of each atom in this. So we have 2 potassiums. How many sulfurs do we have? Yep, just 1. And oxygens? 4. This next one's a little trickier. Again, this is a polyatomic ion with sulfate. We have 3 types of atoms. How many aluminums do we have? So 1, 2. There's a subscript there. How many sulfurs do we have? 3. 3. So this works kind of like if you have multiplication or algebra stuff. If you had 2 multiplied by, we'll say x in parentheses, then you multiply it by everything in the parentheses. So this would be 2x. Similarly, you could also have like 2x plus y. Then this would be 2x plus 2y. So the 3 applies to the sulfur, but it also applies to the oxygen. So we just multiply the things inside. Multiply the things inside by the number of the subscript for that polyatomic ion. So sulfurs, we have 3. How many oxygens do we have? Yeah, 12. You're going to multiply this by, well, that's actually 3 times 4, and then 3, the different color, blue, 3 times 1 for the implied sulfur. Cool. We have a few different types of chemical formulas. There's what's called the empirical formula, which gives the relative number of atoms of each element in a compound. So you could have something, well, let me go over all 3 of these definitions, and then I'll give you a few examples of how these are different. The molecular formula gives the actual number of atoms of each element in a molecule of the compound. This is the relative number, the actual number. So the difference lies for usually larger molecules. Oh, actually, can be some smaller molecules. So the molecular formula, talked about hydrogen peroxide already, H2O2. But the ratio of hydrogens to oxygens is 1 to 1. So the empirical formula of hydrogen peroxide would just be HO, even though the actual molecule has 2 of each. You can have other compounds where it's just let's make something up. Let's say N3O9. So the empirical formula is always going to be a multiple of all of the numbers of them, all of the numbers of the actual formula. So the empirical, well, let me ask this question. What would the empirical formula of this N3O9 be? It's the largest number you could divide both of them by and get a whole number. 3. So if we divide both of these by 3, our empirical formula would be NO3. And we'll cover more about empirical formulas later. We'll even have a couple labs on it. Usually it's used the other way around. It's called the empirical formula because you can easily do an experiment and figure out the relative numbers of the atoms. It takes a little bit more work to get the actual number. The structural formula is really completely different from the other 2 because it uses lines to represent bonds between the atoms. So I mentioned that for something like sucrose, if it's got all these different carbons, hydrogens, and oxygens, those can be rearranged to make completely different compounds. So the order that atoms are bound together matters also. If we had, so structural formula for hydrogen peroxide would be something like this. This would be the actual structural formula. It's the oxygens that are bound to each other, and the hydrogens bound on the outside of those. But you could write an incorrect formula for this, maybe by doing something like this. So changing the organization matters. So the structural formula tells you, all right, these are the numbers of each atom and the way that they're put together, rather than just the number of them. So for some structural formulas, we have the molecular models, which are 3-dimensional representations of models. So it shows you how they're stuck together, but also kind of gives you the relative sizes of those atoms also. And that can be either a ball and stick. So you just have, these are like the typical colors that are used. Or you can have space filling models, which really shows you how much space each atom takes up. So molecular formula for methane. This tells us how many of each atom there are. and it's the molecular formula, so it's the actual number, not the empirical formula. A structural formula shows us that it's the carbon in the middle with the 4 hydrogens bound to it. The other thing that a ball and stick model will show you is the 3D geometry. So this isn't like a little cross. It's more like a tripod. There's the 3 sticking out on the bottom with the little like antenna coming up in the middle. And the space filling model fills out that space between those. Gives you sort of the relative sizes too. So yeah, it helps to try and develop this idea that these molecules that we're talking about look mostly like this, for the most part. And they're in there, they're wiggling around, they're moving around. This helps to visualize what's going on. Because in the macroscopic world, we have no corollary. There's no like real true analog for these things, because we look at a glass of water, you see the water, right? It looks like water, you've seen that your entire life. But if you were to zoom into this molecular level, there are these space filling models of water all bumping around. And then the symbolic way that we represent them as H2O is the most easy to work with. So thinking of things in these molecular levels helps conceptually. Being able to switch then to symbolic helps when you're actually trying to calculate things. So another flowchart of how we're going to break these down into categories. So you remember pure substances from chapter 3, beginning of chapter 3, and we had elements, elements and compounds. And I think when we talked about elements, we talked about atomic elements, molecular elements. But for compounds, we're going to add something here. So we've got molecular compounds, something like water. We also have ionic compounds, which are different. And we'll talk about how to name these also. So the atomic elements are those that exist in nature with single atoms as their basic units. Most elements fall into this category. So if you were to have, elemental iron, that exists sort of as single iron atoms. I mean, usually they're iron atoms clumped together, but they're not a molecule. It gets complicated. We do have molecular elements. There's a few ways to remember these. The one that I remember is Brinkelhoff, Brinclof. Yeah. But there's another one. Oh, wait, no, I missed the O, or the H. Brinkel, HOF. There's another one that's horses need oats or clear brown eyes. So HNOFCLBR. Oh, eyes, but it's letter I for iodine. So whatever silly acronym works for you and helps you memorize those. These ones exist in nature. I alluded to this earlier as diatomic molecules. So you don't get hydrogen by itself. You get 2 hydrogens bound together as a molecule. So similar to like what I was saying with iron, mercury atoms exist as single atoms. You could break these off. You could have any number of them. You could pull off, you had the right tools, you could pull off a single mercury atom. but they're not bound together in any specific ratio. Whereas something like chlorine, which is one of the diatomic elements, or the molecular elements, always exists as these Cl2 diatoms. It's two chlorines bound together. We'll talk about why they do that later. Like chapter, I think it's chapter 11. Oh yeah, see, horses need oats for clear brown eyes. One way to remember them. You can also remember if patterns work better for you. Hydrogen is the one exception to the pattern. And then it's this L shape on the periodic table. So nitrogen, oxygen, fluorine, and then down fluorine through iodine. Right. So most of the halogens, except for I think it's astatine, are the diatomic elements. Okay, so that's the element side of that tree that we were looking at a few slides ago. Right, let me go back to that real quick. Right. So we covered this: elements, atomic elements versus molecular elements. Now we're going to go to the other side of this, talk about our different types of compounds. So we have our molecular compounds, which are formed from two or more nonmetals. Carbon dioxide is one of those. Seen here is dry ice. And then ionic compounds are a little weird because they contain one or more cations paired with one or more anions. They usually contain a metal. But when we talk about these, we do them in formula units. So a formula unit, oops. I think a casual definition is it's the simplest whole ratio, whole number. So salt is like a matrix. It's a lattice. It's a grid of sodiums and chlorines all stuck to each other. But when we talk about salt or sodium chloride, we only talk about the simplest whole number ratio, which is sodium and chlorine. Even though that represents, in any amount of sodium chloride, a large crystal structure. So the ionic compounds, it's a compound composed of a metal. Well, if it's composed of a metal and a non-metal, it's considered ionic. The basic unit of ionic compounds, like I was just talking about, it's a formula unit. So it's just one piece of that lattice, the smallest piece that we can do with whole numbers. Unlike molecular compounds, oh, this is explaining all of this again. Yeah, cations and anions and an alternating array. Trying to think of an example. Analogy. I mean, it's kind of like when you have, you've ever had a lot of marbles, you put them in like a tray and they all stack up really nicely on top of each other. That's kind of what it like what it is, except it's alternating perfectly. I should find a picture of this. Well, I guess, no, that's not a good picture. It's kind of like this, right? How there's always each purple's always touching green and the greens are only touching purple. I need to find a better example of that. So they're, yeah, consist of cations, anions. Positive charge, negative charge. Okay. So I'm going to classify these as atomic element, molecular compound, or ionic compound. So for A, chlorine, atomic element, molecular compound, ionic compound. No takers? Atomic element is a good guess. This is one of the molecular elements. I appreciate your bravery. Yeah, because I mean, atomic element, very good guess, because it is one of those, but it's one of the special ones. So it's a molecular element. Nitrogen monoxide. The biggest considerations here, I think, and maybe one of the things when you're studying this, is try to put these together logically. So if we think about chlorine, chlorine is made up of a single type of element. So we know it either has to be an atomic element or a molecular element. And then to check if that's true, or which of those it is, we just have to check the list of molecular elements. If it's not on that list, it's atomic. For other things, right, our first check is multiple elements, right? Because if it is multiple elements, if we say yes, then it has to be a compound. If the answer is no, then it has to be an element of some kind. So for B here, nitrogen and oxygen, we have multiple elements, so it has to be a compound. Yes, it is a molecular compound. Because our next question would be either, well, I think the easiest next question is, does it have a metal? Neither nitrogen nor oxygen is a metal, so it's a molecular element. So it'd be a compound, and then we ask, does it have a metal? If it's well, I guess I'll start with, if it's no, then it's a molecular element. Yeah. Okay, so good, molecular element, or sorry, something felt off about that. Okay, sorry, molecular compound. So for C, do we have multiple elements? No. Is it one of the special? It is not, because those are only nonmetals. So it's an atomic element. Yeah. All right, how about for D? So we have, do we have multiple elements? Yes. Does it have a metal? Where's sodium on the periodic table? I guess I could pull up the periodic table. So sodium is all the way on the left side. So it is a metal. So we have multiple elements and we have a metal. Because we have a metal, it's an ionic compound. So if the answer to this is yes, ionic compound. How about E? It is also an ionic compound. Yeah, because chromium is a metal. Cr is chromium. Because we have multiple elements and one of them is a metal, this is an ionic compound. There are lots of things that can be broken down to flowcharts like this. The first step, if you can go through the process of making this exclusive kind of flowchart, it's like, what question can I ask that would sort these two things apart? One, it helps you understand the definitions of those things, because you have to know those definitions to make that distinction. And two, it also gives it a structure in your head so that when you do look at a problem like this, the first probably several times, you'll go back to your flowchart, look at that, use that, but eventually you won't have to anymore, and it'll be intuitive. So that's a study recommendation. Try to sort these things. and let me fill this in. The question here would be for the elements. Well, is it on the list? All right, the list of special elements. Yes. Molecular element, no. Okay. So there are ions with predictable charges. The majority of metals that you will encounter in this class will be those with predictable charges. So we talked about this in chapter 4, towards the end there. It's also that list of metals, or this also ties into element quiz 2. Because all of the charges that I'm having you memorize there are the predictable charges. So metals in groups 1A, 2A, and 3A. I kind of want to go back to this one. Right? So we have 1A, 2A, and 3A, predictable, where 1A is a +1 charge, or 1+ charge. 2A is a 2+ charge. 3A is 3+. So it's the same as its group number when we're using the main group numbers. So 1A, 2A, 3A. For the nonmetals, the charge is the group number minus 8 if you count back. So we go back to this. No, go back over here. So 6A, the group number is 6. 6 minus 8 is -2. So these are all 2- charges. 7A, so 7 is its group number, minus 8 is 1-. So these are all 1- charges. And that's pretty much it. I think there's one other that I have you remember. I think it's scandium. So those are the predictable ones. In an ionic compound, we always have a cation, positive charge, and an anion, a negative charge. The proper formula for any ionic compound, those charges will add up to 0. So something like sodium. Sodium is in group 1A, so there's a 1+ charge, or the ion of sodium forms a 1+ charge. Chlorine is in 7A, so it has a 1- charge. So a 1+ charge plus a 1- charge is 0. So these form 1 sodium, 1 chlorine. We're gonna have if we have something like magnesium chloride, so magnesium, chlorine, chlorine again, chlorine only forms 1 charge, it's 1-. Magnesium only forms 1 charge, it's in group 2A, so its charge is 2+. So if we want the charges to add up to 0, we need 2 chlorines. So this magnesium chloride is MgCl2. Because when we add the charges up together, they'll equal 0. Because if we have 2 chlorines, that's 2 1- charges for a total of 2-. Okay, so as a sort of more step-by-step, we start by write the symbol for both ions and include the charges. Make the magnitude of the charge on each ion without the sign become the subscript of the other ion. So magnesium 2+, we'll write out these charges, magnesium, chloride. So the magnitude of 2+ is 2. Magnitude of 3+ would be 3. The magnitude of 3- would be 3. So we're going to take this is called the Crisscross method. Take this, just the magnitude. We're going to make it the subscript of chlorine. Then we're going to take the magnitude of chlorine's charge. We're going to make it the subscript of magnesium. So the subscript of magnesium will be Mg1. So it's implied. So we just I'll write it in. Mg1 Cl2. Because we leave the ones off as implied, we get MgCl2. So this is a sort of an easy way to make the charges match and equal 0 without doing the math. Because you can get ones that are more difficult. I'm sure we'll get an example. The one time that you do need to, well, the next step would be to reduce the subscripts to give a ratio with the smallest whole numbers. So that means if you get something like, think of an example. Well, vanadium can have a 4+ charge, and oxygen is a 2- charge. So we do this crisscross method. We'll get V2O4. We would reduce this to the smallest whole number ratio. So because we can divide both of those by 2, we'll divide them by 2. And our answer here would be, not Y, VO2. And then if you want to, you can write the charges out, multiply them by the number of the atom, and see if they add up to 0. All right, so we want to write something for strontium and chlorine. Just got to go find the symbols. Strontium is Sr, chlorine is Cl. I always forget where if strontium's in column 2 or column 1. So here strontium is in 2A. So it has a 2+ charge. Oops. So we've got strontium 2+, and then chlorine is in column 7A. Yep, 1- charge. So we can use the crisscross method here to balance these, or if it makes sense to just look at them and balance them, you can do that as well. We'll take the magnitude of this, make it the subscript of chlorine. Then we'll take the magnitude of chlorine's charge, make it the subscript of strontium. So SrCl2. You got lots of practice for this on the nomenclature worksheet. Yep, got about halfway. Yeah, let's do this one last example very quickly. So I'm going to write the formula for the compound that forms from aluminum, so Al, and nitrogen. So going to the periodic table, aluminum is, yep, 3 and 3A. Nitrogen is in 5A. So it's 5 minus 8. So it's a 3- charge. So Al3+, and then N 3 minus. So we can do the crisscross method here. And we'll get, right, AL, the magnitude of this becomes that. Magnitude of here goes there. AL3, N3. We can reduce this to ALN. Because remember, for these ionic compounds, the compound is like.
May I have your attention, please? This is IED.
The ionic compounds, this is like a billion aluminum atoms. It's actually way more than a billion, but a billion aluminum atoms and a billion nitrogen atoms. The best way to represent it is with the whole number ratio, the simplest whole number ratio. Okay, we'll cover a truncated version of the rest of this in lab so that you can do the nomenclature worksheet and ask me lots and lots of questions. And then we'll finish it out properly on Wednesday. Okay, so on Monday then, Monday's lab got a little taste of what's to come for this nomenclature thing, and I did move, actually I don't even think I had to move the due date, but the due date for this nomenclature is actually next Friday. So you have a lot of time to work on this. It was there, so I'm gonna leave it there. And after tonight, I will post this video. Chapter 4 is up. I compiled both those separate lectures into a single video. So that's posted, all of chapter 4 in one video. So today we're gonna cover more about how we write formulas from compound names, but also going from the formulas to the compound names, because they go back and forth. So we left off on this polyatomic ion slide. There's a lot of polyatomic ions here. A lot of these can be memorized using some systematic stuff, and we will go over that today. I didn't really go over it on Monday night, or well, it was night, Monday lab. But we'll go over that more here. Okay, so if we want to write a formula for the compound that forms between calcium and nitrate ions, the first step that we talked about last time was writing out the symbols for each of the ions. So for calcium, it's going to be Ca. For nitrate, I think actually if it ends like ATE, ITE, the polyatomic ions, if you don't recognize it as an element, it's probably a polyatomic ion. And you should know pretty much all the elements that we're going to work with after this quiz, the element quiz. So nitrate will be nitrogen, as you maybe could have guessed, and then it's going to be NO3 minus, and the calcium, because it is in, oh wait, I realized I could do this. This thing still has the periodic table on it. So calcium is in group 2. So it has a 2+ charge, right? Because everything in group 1 has a 1+ charge or forms a 1+ charge. Everything in group 2 forms 2+ charges. So you have calcium there with their 2+ charge. And then there are a couple ways that you can attack this problem. The fundamental thing that you need to know is that the charges will balance and add up to 0. One way to do that is the crisscross method. So we can take the magnitude of this charge on calcium and make it the subscript for nitrate. We'll take the magnitude of the charge on nitrate and make it the subscript for calcium. So then it was Ca, and since nitrate has a 1- charge, we leave the 1 off because it's implied. And then because nitrate is a polyatomic ion, we'll put that in parentheses and put that 2 as a subscript outside of the parentheses. And then if we wanted to check these charges, we could say calcium Oops. Calcium has a 2 plus charge. So we have 1 calcium atom times the 2 plus charge equals positive 2. And then our nitrate, which is NO3, we have 2 of those times a 1 minus charge equals minus 2. And if we add these together, there's 0. So I think we did a bunch of examples of that with monoatomic ions. This is how you do it with polyatomic ions. It's really the same process. I think the trickiest thing is identifying maybe that nitrate is a polyatomic ion, and then knowing that you need to go look it up in a table or memorize it at some point. So same kind of question. We want to form a compound between aluminum and phosphate ions. So we'll write out the symbols for these. Aluminum is that, and then when you're memorizing these charges, there's this triangle here: aluminum, zinc, silver, cadmium, indium, and then gallium. So this triangle on the periodic table, those all have consistent charges, at least for the purposes of this class. This column with aluminum, gallium, and indium, they all form 3 plus charges, and there's 3 of them there in that part of the triangle. Zinc and cadmium both form 2 plus charges, and there's 2 of them. And then silver forms a 1 plus, and there's just the 1. So I think I've mentioned this before. Patterns really help me for recognizing where things are on the periodic table and using the periodic table to memorize things like charges. So aluminum has a 3 plus. Phosphate is made from phosphorus and oxygen. It's PO4, 3 minus. So again, we want to balance these charges. And at this point, again, we want the charges to add up to 0. So if this is a positive 3 on aluminum and a negative 3 on phosphorus, we can say we're going to need 1 of each of those to balance that charge. And you'll get the correct answer that way. You can also use the crisscross method. And this highlights an important point about the crisscross method. If we take this 3, put it over here, take this 3, and move it over to aluminum, we'll get Al3 in parentheses, PO4, and then outside of this parentheses, 3. So because those are both have 3 as a subscript, we can simplify that. Because remember, this is an ionic compound. So if you had any amount of this, more than just a single pair, it's actually a matrix of aluminum and phosphates alternating in a giant grid, in a giant matrix. So we always talk about the simplest unit. So we divide both of these subscripts by 3 and still get a whole number. It's the least common denominator. I think it's the least common denominator. Or is the greatest common denominator? Anyway, so then we get Al with a subscript of 1 and PO4 with a subscript of 1. So then we end up with the same answer for both of these. There are just a few more steps with the crisscross method. Just keep in mind that the fundamental thing is we want, or the sum of charges equals 0. I think it's easy to just try and do the crisscross method every time and then lose sight of that fact that that's the ultimate goal. All right, so another one here. We have sodium, which is Na. Sulfite is a polyatomic ion of sulfur. We'll talk more about polyatomic ions. This is SO3, 2 minus. And sodium is in our first column, so it has a 1 plus charge. So if we want to balance these, again, when I look at this, I see that sodium's charge is positive 1, sulfite's charge is minus 2, so I'm going to need 2 sodiums to balance the charge on the sulfite. So we would get Na2SO3. And then if we were using the crisscross method, again, take the magnitude of that charge on sulfite and the magnitude of the charge on sodium, and use those as the subscripts, and that would give us the same thing. Whoops. Two different methods, same end product. So, well, at the very beginning of this chapter, we started talking about how to identify these different types of compounds, which is important because there are different naming systems for different types of compounds. So you name an ionic compound, the ones that we've been doing, differently from a molecular compound. So you have to be able to tell the difference between them. There are a lot of compounds that have common names, or well, some. Water, ammonia. We don't deal with a ton of those aside from these two. But generally, you'll see those common names rather than the systematic names. Oh, there's a leftover from, this is actually ammonium. So the first step in naming an ionic compound is identifying it as an ionic compound. And we could do that by looking and checking if there is a metal and one or more nonmetals together in a chemical formula. We assume it's ionic. The exception is that it's actually a metal or ammonium and one or more nonmetal. So you can group in this ammonium with the metals as ionic compounds. So if we have ionic compounds, for our ionic compounds too, we can break that down a step further into metals that form only one type of ion. And again, those are all the ones on the element quiz 2, which will be in 2 weeks. And then we have all the other metals which form more than one type of ion. So we have to name those differently because in the name we need to indicate what that charge is, or what that ion is. So I have filled in some of these here. Whoops. Another one that's not on here is actually scandium, which is a 3+. So all of these ions, and this is a 1+. All of these ions all of these are the predictable ions, predictable metal ions, the ones that I expect you to know. If it's not one of these, then it forms more than one type of ion. This is again just showing these ones that form single types of ions. This is again that triangle that I was talking about earlier, along with scandium over here. So when that charge is not always the same, we have to indicate what it is. And that we make that part of the metal's name. So we saw, I think actually on an earlier slide, some like ferrous or ferric, cupric or cuprous. So we're not using those because this is easier, which is why these are written in here. So we're not doing those. But iron can have two different types of charges. It can be a 2+ or it can be a 3+. So if you were trying to use this in if you're trying to go from the chemical name to the formula, your formula would end up being different because there's a different charge. Or if the charge wasn't specified, you wouldn't know actually which compound it would be because you need to balance the charges so that they add up to 0. And so we indicate these charges with Roman numerals, which you might need to review. Oh no, here's the slide. So these are the older names, and we're not going to use those. Just focus on using Roman numerals plus the metal name to indicate the charge. So we have monoatomic anions. These are anions containing single nonmetal element, monoatomic, mono meaning one. And when we change these to the ion, we change the ending to IDE. So fluorine is just the element without a charge. If it has a 1- charge, then it's fluoride. Chloride, bromide, iodide, oxide, sulfide, nitride. This is going to be important, of course, when we're going from a formula to a name. You got to know to change that to IDE and not just leave it as fluorine. So for these ionic compounds, the only ones we're going to have in this class will contain only 2 ions. So one cation and one anion. That anion, then, if you see something like, sodium nitrate, you'll know that this is not the metal, so it must be a polyatomic ion. If we talk about only 2 ions, this is a single ion because it operates as one unit. So the cation is usually the first element. And even with, I think this is saying that the exception here is not that ammonium won't be the first element, but it will be the first, it's not a metal. So the exception is the cation is usually first. That's almost always a metal, except when it's ammonium. And then the anion's everything after that. As always, examples are helpful. So what are the names of the elements that form this ionic compound? Yep, potassium and bromine. Yeah, for just the elements.
May I have your attention, please? This is Atlas IED.
Probably get another one in a few minutes. So potassium and bromine are the 2 elements there. And so potassium is our metal. If you remember, everything basically to the left of this line are metals. And potassium's all the way over here. So that first one's our metal, so everything else is the anion. And since we have a monoatomic anion, right, it's made up of just a single element, we'll change that ending to IDE. So we'll get potassium, bromide. All right, so for this next one, what are our 2 elements? Zinc and nitrogen, yeah. So I think it's also important to note here that when we go from the formula to the name, we don't actually need to include how many of each atom there are, because we can figure that out. For these, zinc is one of the ones that forms a single ion. Zinc's over here, forms a 2+ charge, always forms a 2+ charge. So it's always going to be zinc 3 and 2, because that's how the charges will balance. So since zinc is our forms a predictable charge, we leave it as zinc. And then we change nitrogen to nitride. So then if we wanted to go back from this name to the compound, you'd say, well, we have zinc and we have Nitrogen, we say, well, zinc forms just one charge, it's 2 plus. Nitrogen also forms one charge. It's not one of the ones I have you remember, but nitrogen is in 15 or 5A. So we do the 5A minus 8, which I think we'll get to later. That's minus 3, or 3 minus. So after doing the crisscross method,
May I have your attention, please? This is Atlas IED.
after doing the crisscross method, you'd get back to, all right, move the 3 over here, the 2 over here. You'd get back to the original compound that we used to create the name. So you go both ways from the names, yeah. It's not supposed to be capitalized, but I will do that all the time. So I'm not going to mark you off points for it, but technically elements are not proper nouns, so they're not capitalized. So if it's not one of these elements, let's just erase this real quick. Thought I erased everything. So the element forms more than one type of ion, has more than one type of charge, i.e. it isn't in one of the groups that we've talked about. We need to determine the charge on the anion first.
May I have your attention, please? This is Atlas IED.
Because if we can determine the charge on the anion, we know that the charges of the anion and the cation have to add to 0, so we can determine what the charge is on the cation, assuming that the formula is written correctly. All right, so the charges must be 0. So for this one, we have iron, and we have oxygen, so it's going to be iron oxide. But iron is not in group 1 or 2. It's not scandium, silver, cadmium, zinc, indium, gallium, or aluminum. All right, it's out here. So we know it forms more than one charge. So if we take a look at our oxygen here, oxygen, and most of the anions that we have do form consistent charges, is in group 16 or 6A. And the way, again, that you can determine the charge on these is it's the group number, which would be the A version, right? So 7A, 6A, 5A, minus 8. So group number minus 8 equals the nonmetal charge. So you'll always get a negative number. So for oxygen, oxygen has a negative 2 charge. And we know that the charge on iron, how do I want to write this? Let's do it like this. So if the charge on iron is our X, then we know that X plus the charge on oxygen. So the charge is a negative 2 or 2 minus. This is actually multiplied by 3. And then the charge on the iron will be multiplied by 2. We know those have to equal 0. So then it's just a little algebra problem. We have 2x minus 6 equals 0. Then we can add 6 to both sides. So we get 2x equals 6. And ultimately, run out of space, divide both sides by 2, x equals 3. So the charge on iron has to be a positive 3. So this is going to be iron, Roman numeral 3, oxide. If you don't like algebra, most of the time you can do the crisscross method in reverse. So you take the charge on, or the subscript for oxygen, or the anion here, and you make it the superscript for iron. So if this is Fe2, O3, we can take this and say that iron is going to be a 3 plus charge. Oxygen is a 2 minus charge. So this should be 3 plus, 2 minus. There are situations where there's actually one that came up in somebody's homework. Let me do this real quick, add a page. Yeah, so if you have something like tin oxide, if we do the crisscross method here, we'll get, or the reverse crisscross. Right, so we'll put this 2 here, and then there's an implied 1. Let me do that in a different color. There's an implied 1 here. Eraser, please. There you go. So we move that implied 1 up here. So then we'll get,
May I have your attention, please? This is Atlas IED.
you'll end up with tin 2 plus and oxygen 1 minus. So this is the sign that this is not quite right, because oxygen always forms, in this class at least, a 2 minus charge. So you actually have to multiply this by 2. So the tin here actually has a, you have to multiply it by 2, because multiplying the 1 minus by 2 will give it a 2 minus. So this tin is 4 plus, and oxygen is 2 minus. And from this, we can see why we get this result. Because if you do the crisscross method from here, we'll put this here, we'll put that there, you'll get tin 2O4, which simplifies by dividing by 2. So just remember that the charges always have to add up to 0. And the anion charges don't change. Do you need more time to write that down? Please let me know if you need more time on slides. Okay, any questions on this so far? And keep going, do more examples. Yeah.
So for this specific problem, you said that you need to multiply by 2 because, like, say you use the crisscross method, it wouldn't make sense since oxygen always forms a -2 charge.
Yes, it's because oxygen always has a 2 minus charge. So the reverse crisscross method, you have to have that extra check to make sure. Yeah, so this method probably more reliable to just go through and do the math and calculate it based on the number of oxygens. And actually, I should do that for this problem too. Right? So if we had this SnO2, we'd say, all right, tin, not one of our elements that has a consistent charge or a predictable charge, but we know that oxygen is 2 minus. So again, if we do it like this, and we say tin, the charge is X, oxygen, our charge is 2 minus. Then we can say the subscript of N here times X, right? So 1X plus the number of oxygen atoms times its charge. So 2 times a -2 charge has to equal 0. Then we'll get X plus -4 equals 0. And then adding 4 to both sides, X equals 4. So this one will give you the correct charges every time. Any other questions? Okay. Keep moving. All right, so if we want to name these compounds now for these cations that form more than one charge, again, same thing that we were just doing. What is this first element? This is not one of the ones I had you memorize. Plumbum, or lead.
May I have your attention, please? This is Atlas IED.
And then oxygen, as an ion, its name would be What do we change the ending to? Yeah, so it'd be oxide. And that one kind of, for some of them, it's not immediately clear where the ending goes, which letters you drop off. Oxygen usually gets abbreviated to ox, and then you change everything after that. But since this is a metal that we need to determine what the charge is, we can do the same thing that we were just doing. We can say that lead is a charge of X. Oxygen is a charge of 2 minus. So X, again, times the subscript, which is 1, plus oxygen, so there's 1 oxygen times a -2 charge. Those have to equal 0. So X plus a -2, 0. So X equals 2. So then we can just fill in here that lead has a 2+ charge in Roman numerals. So for this next one, does anybody know what the first element is? Copper, cupric. So copper, again, doesn't fall into the list of all of the metals that form predictable charges. And then this is sulfur, but it's an ion, so it becomes sulfide. And again, we can set up the same math. So we have copper with a charge of X. We have 2 copper ions. And then we have sulfur. What charge does sulfur form? So it's in 16 or 6A? 2 minus. Yeah. So it's a 2 charge. So then we'll do 2 times X plus 1 times the -2. That was 0. So 2x plus a -2 is equal to 0. Ran out of space. So 2x equals 2. So x equals 1. So the charge on copper is just 1. And that's a Roman numeral, not a 1. Again, it all just kind of comes down to finding what that adds up to 0. Yeah.
I have a question. So are we using the Roman numerals because they're transitional metals? Or, like, is there a reason why we're using Roman numerals?
I think it's just like the standard that they've set up. When you're writing a name out, use the Roman numeral instead of putting a regular number in there. It's a good question. I don't know if there's another specific reason for the Roman numerals. Yeah. I'm gonna have to look that up. Little Google foo. Okay, so oxyanions. Most polyatomic ions are oxyanions. There are a lot of them, but I think they're easy to name if you can remember the rules for naming them. So you can memorize, for 7 of them, you can memorize, let's see, 4 times 7. So there's like 28 of them total, but you only have to memorize 7, and then the couple rules for changing the number of oxygens. So they have, and the reason for that is because they have systematic names. So you memorize the ones ending in ATE. Those are the, what I call the base form. And one of these rules is that when the ending is ITE, that's 1 fewer oxygen than the ATE form. So for nitrate, that becomes nitrite. And a key thing here is the charge doesn't change, but it has one fewer oxygen. So it goes from NO3 to NO2. For sulfate, the base form has a different number of oxygens from nitrate, but the same rule applies in that when we change that ending to ITE, we just drop one oxygen, and it still has a 2- charge. We call it sulfite. A lot of these have more than one ion in the series. So there are a couple other rules that we use. So if we have one fewer oxygen than the ITE form, that's hypoite. So I'm going to actually write these rules out up here. So if we have the ATE, that's our base. I guess I should do it the way they have it here. If we have ITE, there's not enough room. All right. So ITE is the base minus one oxygen. Hypo ITE, where the name goes in the middle there, is the base minus 2 oxygens. And then we can have per ATE is the base plus 1 oxygen. All got cut off. Huh. That's a little better. So for all of these, we have chlorate, that's our base form, which has 3 oxygens. Chlorite, right, so it's base minus 1 oxygen, ClO2. Same charge, 1 minus. Then hypochlorite is ClO minus. Right, we've taken 2 oxygens away from the base form. Again, same charge. Then if we add to the base form per at the beginning, then we get perchlorate. That's ClO4 minus. So we've added an oxygen to the base form, keep the same charge. And that works for actually over here on this periodic table, that works for chlorate, bromate, and iodate. And these all have 3 oxygens in their base form. So these 3 oxygens in the base form. Phosphate, sulfate, arsenate, and selenate all have, so those 4 have 4 oxygens in their base form. So if we wanted per sulfate, then we would add the SO4, we would add 1 more oxygen, the SO5, 2 minus. So again, patterns on the periodic table. That's how I remember these. And then the charges also follow a pattern on the periodic table. Chlorate, bromate, and iodate all have a 1 minus charge. Sulfate and selenate have a 2 minus charge. Phosphate and arsenate have a 3 minus charge. Just like the column that their base element is in and the charge that those would form. Those rules are all laid out on the study guide for the polyatomic ion quiz. So it'll be helpful for remembering these things as you go through, the rest of this class. Any questions about that? take some time to just work through those rules. So a lot of these actually end up being household products. Sodium hypochlorite is bleach. Right, so it kills bacteria, also destroys color-creating molecules, or causing, I guess. Sodium bicarbonate is baking soda. Calcium carbonate is the antacid in Tums or alkamints. Sodium nitrate is a preservative, nitrite, ITE, is a preservative for packaged meats and inhibits the growth of bacteria, especially ones that cause botulism, although now it's kind of come out that you should probably avoid nitrites in preserved meats. So they usually leave them out now and they use something else. Okay, so if we want to name these compounds, really all of the same rules apply that would apply to ionic compounds. You just have to remember the names of the polyatomic ions. So for this first one, you know what this first element is? Manganese. Makes a really nice purple color. So manganese is not on our list of ions that form consistent charges, so we can just throw a placeholder parentheses in here until we figure out what that charge is. This NO2, which sort of given a hint that that's a polyatomic ion, in that it's in parentheses. So in addition to the 7 that I pointed out here, nitrogen and carbon also form polyatomic ions. So it's nitrate and carbonate. Their base form has 3 oxygens. So if the base form of this is NO3, and for nitrate it's a minus charge. So if this is the ATE, we have NO2, so 1 fewer oxygen. So NO2 minus, let me write out the name here, nitrate. So it's the light form, has 1 fewer oxygen. It's nitrite. So this is manganese nitrate. And then we can solve an equation for manganese's charge. So if we want to do that like we were doing before, it's manganese, right, with a charge of X, and then NO2, actually 2 NO2s, with a 1 minus charge. So our 1 manganese times its charge plus our 2 nitrites times their 1 minus charge will be 0. So X plus a negative 2 equals 0. X equals 2. So manganese must have a 2 plus charge. So for this next one, we have, any guess what this one is? Cobalt, super important metal for making touch screens. But cobalt is also a transition metal and not in our list. So it'll have some charge that we'll have to determine. And then CO3, right, is the polyatomic ion of carbon. And its base form has 3 oxygens. So this is carbon 8. So it's cobalt carbonate. And important here to point out too that this would not be cobalt carbide, because carbide would just be COC, with however many carbons that would be. So the IDE versus the ATE tells you that it's something is important and is something else. So carbonate has 2 minus charge. Cobalt has the charge that we want to determine. Actually, just based on this information, what is the charge on cobalt? if we have a -2 charge from carbonate, we only have one carbonate and one cobalt. Yeah, it's a 2+ charge. So especially in simpler ones like this, where it's just 1 and 1, the charge of the cobalt has to be exactly the opposite charge of the anion, in this case carbonate. But again, multiple ways to get to the same answer. So 1x plus 1 times a 2 minus charge has to equal 0. So x plus -2 has to equal 0. So x equals 2. Actually, almost-ish. Right, we're at 54-68. Okay, so that was ionic compounds. Naming ones that have predictable charges, naming ones that have unpredictable charges, how to figure those out. Naming molecular compounds, by comparison, is much easier. So the first step for any of these, really, is identifying it as the type of compound for the naming scheme we're going to use. So molecular compounds are made up of 2 or more nonmetals. And again, in this class, like the ionic compounds, we're only going to learn binary or 2-element molecular compounds. In these compounds, we have special prefixes, and the prefixes indicate how many of each element there are. For the first element, we just leave it as its name. For the second element, like we did for the ionic compounds, we change that to IDE. So these are the prefixes: mono, di, tri, tetra, penta, right, all the way up to 10, deca, indicating how many of those there are. So I think actually, I don't know why this was so much earlier. Let me go back to this. Wait, let me bookmark this slide first. And we talked about the order in which you place elements way near the beginning. Yeah, here we go. Okay, so when we're organizing these, you might ask, well, which element is supposed to go first? Comes all the way back to this table, really. Or choosing which one's the most metallic. So all the way left on the periodic table, these are the most metallic elements. On the right side of the periodic table, the least metallic elements. So for the nonmetals, carbon is more metallic than nitrogen. And nitrogen is more metallic than oxygen. Going up and down gets a little bit squirrely, but as we can see, we go carbon, carbon, phosphorus, nitrogen, then hydrogen, sulfur, iodine, bromine, chlorine, fluorine. So the order is a little bit weird, but you can always refer back to this table for that order if you need it. Oh. So in this element, though, we have carbon dioxide. And again, we leave a lot of ones off. So monocarbon dioxide, while technically may be correct, it's not like wrong, but you don't need that mono there. So if you have the first element and just one of the first element, all right, one atom of the first element, prefix mono, is dropped. So mono here is 1, di is 2. And then if the prefix ends with a vowel and the base name starts with a vowel, the first vowel, and I hate this, is sometimes dropped. And this is one of those things where if you know the prefix and you know the base, you can Google it and figure out if it's supposed to be dropped or not, if you really want to be that correct about it. I'm not going to mark you off for, right, so this is dinitrogen monooxide, or sorry, not monooxide, it's monoxide, because you would have two O's right next to each other if you had monooxide. So generally this, one of those O's gets dropped. So let me write at least these ones that we're going to be using. All right, we have mono, which is 1, di, which is 2, tri, which is 3. Tetra was one that I always forgot, is 4. And that'll get us through these at least. So for our first compound, what would the name be? If anybody wants to just go for it. What was it? Good start? Oh, yeah, because it's a nitrogen and an oxygen. It's an interesting point. Here, because it is 2 nitrogens, it's not going to be nitrate, because nitrate is always, or nitrate, nitrite, those are always a single nitrogen. But yeah, I like where your head's at. This would be dinitrogen, but it would just be dinitrogen. And what would the prefix for oxygen be? Tetra. And this is one of those cases where you drop a vowel. It's tetroxide. And then again, remember to change that ending of the second element to IDE. How about for this next compound? How do we start naming this? Mono? Yeah, it would be mononitrogen, but usually we drop the mono for the first. So it'd just be nitrogen. But you're right, mono meaning 1. And then for hydrogen? Tri. And then I think this one is a little weird. It's high dried. So you're kind of writing all the way up to, because it would be hydrogen, you leave out the ogen and put the IDE there. So the reason that we need to say how many of each element there is in a molecular compound is because we don't have a rule like charges to figure it out. So you have to say explicitly there are this many of this and this many of that. Otherwise, there's no way to figure it out. If you just wrote nitrogen hydride or nitrogen oxide. All right, the last couple categories here are acids. We have 2 different types of acids that we're going to learn how to name. And again, I think like compared to ionic compounds, everything just gets simpler. Right? So for molecular compounds, you just need to put the number using the special naming number names, and then change the second one to IDE. For acids, there's 2 types, binary acids, and there are oxyacids. And the way you identify something as an acid is hydrogen is the first element in the formula. So if you get HCl is an acid, or HNO3 would be an acid. Binary acids will be hydrogen and a nonmetal. And so we have hydrogen, nonmetal, so this one is a binary acid. And then oxyacids will be hydrogen, a nonmetal, and oxygen. They'll be the oxyanions that we talked about earlier. So for binary acids, again, if you say, or if you recognize that there is a hydrogen first and then a single nonmetal second, right, composed of just two elements, you'll add a hydro to the front. You'll change the base name of the nonmetal plus IC, so that ending changes to IC, and then put acid at the end. So HCl, we have hydrogen, chlorine, so two elements. So you put hydro, right, that's the hydro, and it'd be chlorine, but we change the ending to IC. So chloric, that's this part, and then we put acid on the end. There's not really that many of them. You can do hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. Yeah, that's kind of it. So really, yeah. So you might even just memorize all of them because we have half of them right here. Those are binary acids. Yeah, a couple examples here. So HF, so we have hydrogen as our first, so we know it's an acid, even though, of course, up here it says naming binary acids. It's an acid, and it's an acid of fluorine. So first step is hydro, and then change the ending of fluorine to fluoric. Acid. Oh, there's another one. But what would this one be? Or what's the first part? Hydro. Se is selenium. Hydroselenic acid. Yep. The only thing that makes the oxyacids tricky is that you have to know the oxyanions, because their name, the name of the oxyanion, affects how you name the acid. So oxyacids contain oxyanions, found in the table of polyatomic ions. So for example, here on this first one, we have hydrogens first again, and then this is nitrate, this is sulfite, this is sulfate. And the number of hydrogens will always be the same as the charge of the oxyanion. So sulfite has a 2- charge. It'll have 2 hydrogens. Sulfate also has a 2- charge. It has 2 hydrogens. So another one that's phosphate, which has a 3- charge. So that will have 3 hydrogens. So that part's easy enough. When it comes to naming these, you have to be aware that we have 2 different endings. We have ATE endings for the base form, and then if you remove 1 oxygen, there's the ITE form, and those get named differently. And they have to be, because you have to indicate if it was before it was an acid, or if the base of the non-acid is the base or 1-. So for ITE, we change it to OUS. Swap it out. For ATE, it becomes IC. And then notice that oxyacids do not have hydro in front. So if you're asked to convert from the name to the formula, if it has hydro in front, it's a binary acid. If it does not have hydro in front, it's an oxyacid. So here are some of these names converted. All right, so nitrite, the acid name is nitrous. so on and so forth. I guess the one weird one on here is acetic acid, which is vinegar. The base of that will be acetate. That is one of the ones that's on the polyatomic ion quiz. All right, so now we have hydrogen in front, but we have more than one non-metal after that. So we know it's an oxyacid. Also the fact that it contains oxygen. So what would the name of the base oxyacid formed from nitrogen be? Whoa. So if it's nitrogen, it would be nitrate. So that would be the base form. The base form would be NO3 minus. So then we have one fewer oxygen than that. So this would be nitrite, NO2 minus. So then when we name this, we got to go back and see ITE, we convert to ITE, convert to OUS. So this would be nitrous acid. The base form for an oxyacid or an oxyanion formed from chlorine is chlorate, and that's ClO3 minus. Because we have one more oxygen than the base form perchlorate. So it'd be ClO4 minus. So ITE we convert to OUS. ATE we convert to IC. So this is just perchloric acid. Again, no hydro. So really, you just keep whatever most of the base name is and change the ending, and then add acid, that names it as the acid. So the hardest part of naming oxyacids is knowing the oxyanions. And for now, you just use tables for those. And in case you were worried about it, I won't expect you, at least I won't expect you on purpose, to remember the names of oxyacids for this first exam, because that's chapter 5. So yes, if I do that, then somebody ask me because I did it on an accident, and I'll put it on the board or write it down, or it'll be written in the question.
So it's going to be 1 through 4?
Chapters 1 through 4. Yes. And this is the super useful chart at the end of this chapter. So you can use this as a flow chart to determine what type of compound you have. So, right, if it's got a metal and a nonmetal, if it's just nonmetals only, if it's hydrogen and one or more nonmetals, and then work through this. And at the end of each of these, you have the naming schemes for each element, or for each type of compound. Going through this flow chart, oh, sorry, you have to do formula mass. Feels so tacked on to the end here. So using this flow chart, you would, look at your compound. You'd say that it's ionic because, well, ionic compounds, I'll have to adjust this so it doesn't cut off the top in the future. Ionic compounds are formed from a metal and a nonmetal. So you would go over here and say, hey, calcium, fluorine, metal, and a nonmetal. It's only one type of ion, because calcium is in, I don't know if I'm pointing at it right, but it's in column 2A. So then we can name it using that scheme, which is this one. So it's the name of the metal cation plus the name of the, or the base name of the nonmetal plus IDE.